Hey guys, welcome to Algo. Hey guys, welcome to AlgoYogi. And before we begin studying trees, I want to introduce you to this web app that I've been building for the last couple of days. And here it is, AlgoYogi.io. This is an amazing way of tracking your lead code problems, doing some mock interviews, learning Python, playing around with some of the DSA topics. But the most important feature here is practice problems. Okay, so let's go over the features of AlgoYogi.io. Okay, practice problems, mock interviews, code gym, and Python. So this is an app, is still in progress, but one feature that's almost wrapped up is practice problems. And let's sign in. If you're watching this video, please sign in. This is the only way to mark your problem solved here, like this. If I'm not signed in, then it's not going to save the data in the database of these problems marked solved. Now, you can group these problems by categories, and if you mark these problems solved by going to LeetCode, you solve them there, come back, mark it solved, then it will track your progress on the progress bar as well, on the overall section, and also in that particular category. That applies to the difficulty level and random also. But then we have mock interview section. You can start interview. It will fetch a problem for you that it has in our database right now. And it will you can solve your problem here. But the thing is, here you will not have the features like LeetCode. You will not have auto-populated examples, because in a real interview, they're asking you to code the solution on the code editor, and they're just asking you to basically run your solution. Most likely, they're not going to ask you to run the solution that you have written. It's just going over one of the examples, that they have given your edge cases, that you need to do it yourself. You will run the code. It will do it for you here. Okay, let's start with our first topic, trees. If you're not signed in, please sign in, come to Code Gym. You can have it on side. And as we are studying, so I'm not a teacher. I'm just a developer who is here as your buddy to solve the problems together. Okay, so let's study trees. And then we will be going to our practice problems. And on the tree section, we will be solving all these problems immediately after covering the trees DSA. And the reason that I'm choosing trees as the first topic to study together, the reason is they're very limited problems and patterns, and most of them are around binary trees or binary search trees. And it will take maybe like a week or maybe less than a week to solve all those problems that I was showing you guys here. And it was the trees. And that's it. Let me just unmark these problems because I haven't uploaded the solution over here for these problems. Let's go over trees now. Okay, if this might seem as a quick revision, and I'm seriously, as I said before, I'm not following any script. It's unscripted teaching. I don't know. This is my first video, and I'm just studying myself with you guys as a buddy, and yeah, and trying to have fun. It gets boring when you just sit down. Like, let's not be so serious about studying these fun topics, right? Let's make them fun. Okay. Trees, as you have seen, it's a non-linear data structure, right? Now, what's a non-linear data structure? So far, what we have seen, such as, let me increase a little bit so that we can focus here more on the content right now. So arrays, linked list, or list, and what else? These are the data structures which are where we store our data in a linear pattern, right? Like either you follow the index, or in linked list you're just following the nodes one after the other using the next pointer. What we are really doing, and stack is also a linear data structures, and they follow basically a pattern. The data will be one after another node, or it could be at a particular index. So in that way, it's very linear. Now, tree, just like you see a tree around yourself, right? Like in your backyard. However, when we are studying as a data structure, just imagine it like inverted tree, right? So you're going to have a root, and then it branches out until leaves. And at every part, where there is a branch out, you see some data stored in that inverted tree. And let's go over the terminology. So it's a non-linear data structure, and it's basically a collection of nodes. What is a node? Node is we can call it like the smallest entity of a tree data structure, right? So node will have the information as like the data or value we usually call, or and then the information about the children of that particular node, and then those children, they're also node themselves that will have further information down the tree for next nodes. Those are that node's children, and also the data that particular node is supposed to store. So it's a collection of nodes, and those nodes, they have information about they might have information about their parent and also the child. Now this is what is this is what a tree looks like. Okay, I don't know. I'm laughing. Yeah. So okay, this right here is root, and root is the node that doesn't have any incoming edges, right? So this is an edge. Edge connects one node to another, and we can say a parent node to a child node. Now, root node, the reason it's called root node is that it doesn't have any parent, right? Just like a tree's root, it is the reason that the whole tree has been since germination, it's been branching out, but the root stays where it is. It's maybe you could just say the first origin of the tree, right? Now, and then you have a root, and then you have the edge that connects to the node, and then it keeps branching out, keeps going down until the leaves. The last node also, that the last node that do not have any children, they are the leaves node, right? That's a leaf node or the leaves node. All of these are leaves nodes. And other terminology that we can also see when we study non-linear data structures, then graph is also a non-linear data structure, and there are certain differences that are there in a tree and a graph. And a graph can contain loops. A tree is not supposed to contain loop, right? Leaves or some nodes in between, they cannot connect with each other. Otherwise, it will be a graph. If 2 was connecting to 3, these two nodes, which are child nodes of root, then it will become a graph, right? It will become a graph. It wouldn't be considered a tree. So it cannot contain any loops. Now let's go over the terminology here. So we have a parent, children, sibling, and sisters and descendants. These are the relationships that we see in a tree. Now, parent is a node that has children, like starting with root. All nodes could be parent unless they do not have any child nodes. Now, children are basically the first descendants. Descendants are the one that occur later after the root. So all of them are descendant of root node 1. 2, 3 are descendant of 1. 4 is a descendant of 2. 4 is not a descendant of 3. And 4 is not a descendant of 5. But 6 is a descendant of 1, 2, 3. So if you follow a path from that root, from that node, X, we could call it X, and if you go up to the root, all the nodes that will be there in that path, they will be the ancestors of that particular node X. And if you follow from the root and then come down, then they all will be the descendants of the root. These are all descendants of root. 2's descendants is everything that's under 2. 5's descendants are all of these. Now, okay, siblings are basically siblings. I mean, these are pretty self-explanatory things. Now, tree is also called a recursive data structure. Along with non-linear data structure, it's also called recursive data structure. And the reason it's called recursive data structure is it could be broken into subtrees. One tree could be broken into subtree. And the way we mostly access the data or solve the problems around a tree, if they are being done using recursion, they're basically first broken down into these smaller chunks of problems, and then we solve them and move up to solve the bigger problems. Okay, look, see, here we have this root, and then we have all these children. But if you just forget about the root and go to one child node, then that node itself is also a tree itself, a full tree, complete. Let's not go over these terminology, complete, full, and those three, but let's just call it a tree. This is a tree. This is tree 2 or tree 3. But then together itself is also one tree, right? Now, let's go over some facts of tree. If there are n nodes, then there will be n minus 1 edges, maximum n minus 1 edges. And not maximum, I think they will be, because root is not receiving any edges. And if we are connecting all the nodes together, then in one or the other way, then there has to be one edge connecting that node to its parent. Now, what is depth of one node? So it's defined as number of edges in path from root to X. And what does it mean? Let's go over here. So if I want to find the depth of 5, which is an X, so the number of edges from this to the root, from root to X, or we could do the other way as well, but from the root, from 1, if we come down to 5, then there are 2 edges. So that's the depth of that root, that node, which we chose 5 here. So 5's depth is counting the edges from the root to 5. Okay, and the similar way, what's the height of X? X height will be counted from the bottom, which is the leaves node. So it's the it has to be the maximum number of edges in the longest path from X to a leaf. So here, right now it's 1. But let's say from 8, we had certain more nodes connected down. It had some children, and then they had more children. Then we'll have to find the longest path to a leaf from 5, and that would be its height. The depth is, just remember, depth is from the root, or the number of edges that we count, and the height is from the longest path until a leaf. Okay, we will go in deep when we will be solving the problems on our practice section, but here just like covering these. And the way we define a node is in Python is having the node class, and it's going to have a value. And currently it's not, we're talking about general trees, not binary tree. I know a lot of problems on LeetCode or what usually interviewers asked are around binary tree or binary search tree. However, to begin with, like, we have to understand the general concept of tree. So in general concept, it's not going to have a left or right node, or right child or left child. It's going to have a value that a node stores, and that self node will have some children that it's going to be storing. It could be none, or it could be just an empty array, because one node in a general tree can have multiple children, right? Now, let's go over to our binary tree. That's what we actually want to study, right? Now, in a binary tree, each node can have at most two children. At most two children. It can have one child, but max it can have two children. And because it can have max two children, now we can say left and right child, right? Otherwise, in a general tree, we don't have a way of saying, okay, this is left, this is right, this is middle, this is... It's usually called an array. Those childs are stored as an array. Even the parent, although it's just one. But anyway, here, now, then we still have a root. We have left child, right child, and then we have these levels. In general, in a tree, we have levels. Level 0, that's where the root is. Level 1 is, that's where like our first, if we go over like, in a BFS search, breadth first search, all the nodes, one distance away, one edge away from the root, that are level 1. Level 2 is 2 edges away. Okay, and here in our binary tree, if we make some modifications, then the reason that I was saying that, okay, let's not say complete tree or perfect tree or full tree or something like, because in tree theory, we have these reserved keywords. Also, they're not really reserved, but conventionally, somebody has just defined these trees, and we don't need to worry too much about it. Just let's say sometimes they come up in a problem, and we kind of expect it to know these definitions. Okay, so complete binary tree is a binary tree where all the levels except the last one, and it has to be completely filled from the left. So what it is trying to say is all the levels except possibly the last one are completely filled, and all nodes are left as possible. So here, if we say is this a complete tree? It's not a complete tree, because there is this level on the last level. This node, if it were over here, then it could be a complete tree, because they have to be filled from the left to right. And all the levels above that, except the last one, have to be completely filled, right? And then what's a perfect binary tree? All levels are completely filled. This has to be completely filled. That's a perfect binary tree. Now, okay, those were not so important, but what's really important is our tree traversal. And what's a tree traversal is visiting all our nodes and printing somewhere, or just processing these nodes or their values in some way. Because at the end of the day, we will be solving these problems, right? We'll be working with the data. We might be adding some nodes in the path, the longest path or the shortest path or whatsoever, or just adding the values of order, all the levels, combining those values and just printing an array. So at the end of the day, we will be doing traversal over a tree. And there are basically 4 kinds of traversal that we can do on a tree. Right now we're dealing with binary tree, and those are the trees that are mostly asked in an interview, so let's just stick to binary tree. However, when we will be solving the problems, we will definitely come across an array tree, and then we will work around it. So in order traversal, the special thing about in order traversal is we visit the nodes in left, root, and right order. And what does it mean? It means first we go to the left child, and then we come to the root, and then we go to the right. So left, root, and right. So if we were to do the in order traversal on this tree, which is a binary tree, then it will be done going to the left. Does it have any left or right? No. Print it, go back to the root, do the root, process the root, and then go to the right. Now, to remember this, just remember in. In is basically you have to be, the root is our main node, right? So all these, kitcher pitcher that we're doing is around root. And root has to be in the middle, so it's in. This I studied some time back, like, this is an easy way to remember it. And having root in the middle, left, right, this is how we traverse, left to right. There will never be a case in any of the traversals where we have right before the left. So it's always left and right. Just remember left, right. Now it's the root. Now it's the root that we are fitting around left, right. So in order, we put the root between left and right. And then preorder, bring the root before left in the front because it's preorder. And root, so if you are traversing over this tree, then root is 1. So it has to be 1, and left is 2, and then right is 3. Okay? Postorder, post is something that's followed after we're done left and right. So left, right, and root. I think it's really clear, right? I don't think we have to do too much around this. So, and then it's left, right. So left and right, and then root. And then one of the most important traversal, which is level order traversal, also known as breadth first search, BFS, is going order by order. First level, 0th level, first level. So 1, 2, 3. Easy peasy. Now, just to go over, because that was a little simple, right? We should do it over here as well. So first example, we just want to print the in order. So we start with the root, which is 1, and then we go left. But now this is also, because it's a recursive data structure, then this in itself is also a tree. So we have to process this one now. Now in this tree, we again do left, we go left. Now this is the leaf node, doesn't have anything, so this has to be processed. This was the left node that we were supposed to, or the tree that we were supposed to process. So then we're gonna print 5, go back to the root. We are now supposed to process the root, which is 2, and then we go to our right. Once we are done processing this subtree, which was also the left of our root 1, then we go back to our root, right? And then we print our root 1. And after that, we go to our right, 3. Again, root left, right is for the preorder. Preorder, root in the front. So we'll start with 1, and then we go to left, this subtree. 2 is again a root, so we're going to print 2, and then go to the next left. Now we're going to process the left because it's the last node, right? So 5, and then process right, 6, and then go back up, go to the right, because we are done processing root and left, go to the right. Post order, same way. You're smart enough, I'm sure you'll do it. It's left, right, root. So go to the left, 5, right, root, not this, right, and root. Level order traversal is going to be just 1, 2, 3, 4 is not there, 5, 6. Okay. Now, before we go to the binary search tree, I just want to do some implementation for you guys. Binary search tree is like a little lengthy topic, because it has some little complex, little more complex than the previous topics. Now, before we go to the binary search tree, I want to show the implementation. Okay, so let's move to our implementation now. Enough theory that we have covered. Currently, we have support in our AlgoYogi for JavaScript and Python. We'll be adding more languages later. For now, I'm sorry if you're using Java, C++, or some other language. We will definitely add support soon, maybe coming week. But now, it's Python it is for now. Okay, so first, to implement a tree, we need the node class. So let's create our, let's call it tree node class. We will have a constructor which will we called init. It's going to take a value that will go to any node we are creating, and then self dot value will be that value, and then it's going to, because we're creating a general tree data structure, a general tree node, so it's not going to have left or right. We will come on to that, the binary tree, later, but for now it's going to be children, which will be an empty list or array right now. Then we can define another function. We can call it add child, and add child is going to take the child, right? The child node. We can call it child node, and then it will add self dot children dot append our child node. All right. Let's also define a simple display function, which will will take the level, but also have the level 0 as a value if it's not passed. We're gonna print 4 spaces, like space into level into 4, and then we'll stringify the value, self dot value. And for now we have to print all the child. We have to it's a recursive function, right? We are printing the self value, which is the root node. It will come. I know it might get a little complicated right now, but like just don't think about it right now, let's call it children, and we will just child.display, and we'll pass the level +1, the next level we are calling. Okay, starting with 0 and then calling. Okay, so now we have our tree node class. We have this basic entity that we use. We have this template to create something. We have this template, and now we use the constructor of tree node to define our variables that we will link with each other to create our general tree. So to begin with, let's call our root. Maybe we can implement something like this here, right? And that's one of the reason I had this side by side this content here, so that we have easy access to the theory, and then while we are implementing, we can easily convert it into a code. So there is no gap in theory and implementation. So let's call our root. So root will be tree node, and then we are passing the value 1. So this is our root right now. Now these are our child nodes, so we can just define them as child 1, and child 1 will be a tree node in itself, and we can call it, we don't have to call it, we'll just, it is what it is. Oh my god. Copy and then paste here. So this is 3 now, and now our root will take add child, and we will be adding child 1, and then we will also add child 2, which we forgot to change the name here. We added the value 3 but forgot to change the name here. Now we have added this, and you know what, We will add these later, but let us use the display function. We have our root, and we can just go and just print the structure of our tree that we have created. So we have root, and then it has two children, or not child, two children. So let's print, and I mean, we don't have to print it actually. We have the print function over the root dot display. This is the reason I created the display function here. Okay, let's run our code. So you see here, this is the root, and then we have our 2 and 3 as root's children. Okay, now further, this child has 2 more children, so we can create child 1 of child 1.1. we can call child 1.1 let's call it like that, and it will be a tree node. I mean, I don't know why I'm just copying it. Let's just call it 4, and then the same way we will have child 1.2, and that will be 5, and I will have to append it to our child 1, that was 2. So child 1 dot children dot append. Oh, sorry. So we can use the function directly. Child 1 dot we, you know, like, this is the reason we had this add child function over there. Now we're gonna add both of these to our child 1. We're not doing rest for now. I mean, the basic point of implementation is so that we understand what's going on in theory, and then what we are doing in practical implementation using Python. So if I will display now, if I call the display function now, let's run our code. So here you see this hierarchical data structure, this hierarchical implementation of having the root having the second level will have 2 child. That's what we have added here to our root, and then to our child 1, which is over here, we have added other children to it, which is 4 and 5, and we could add to the 5 as well, and then it will show in this. I'm using this 4 as, like, you know, showing enough gap between the root and then its children. Okay, now so these are the children of 2, so they will display at the same level. Okay, because level will be going same value for it, and which will be like 1, 2. Initially it's 0, and then 1, and then 2, and then this will be around like 8 gap of space. Okay, so this is our general tree. Now it's already like we have covered these topics, and this is here we are doing it recursively, by the way, because this is like this display function is more like a DFS, depth first search, is taking the root, processing the root, and then before going to the other children, like, we just go to the one child, pick up that child, and call the function on that particular child, and then when that finishes up, then you process the next child, right? You just keep going in the depth of that that node, particular child node, and then keep going down until it doesn't have any children, and then come back up one more level up, and then process all the child over there, and then more one level up, and then process all the child over there. So I think now we are good to come to our binary tree. So we have to modify our tree node for binary tree because it doesn't have children anymore. It has left child and right child. I mean, we can fit a normal binary tree into a general tree as well, because instead of left and right, we can just add both of them to our children. But if you want to, you know, like, remove that abstraction from there, then you're going to have left left child. Initially, let's say it's gonna be none when there's nothing over there. Then right child will also be none. Let's get rid of our add function, because this time we can simply just assign left and right to the root or whichever node we are at. Display function, we have to modify it. Level we can keep, and this we can keep, but no longer we will have this. No longer we will have this children. We will be checking for if left or right, you know. So let's add another thing here. We can call it let's call it prefix. Prefix will be initially prefix will be root, right, root, and then we can send left and right later. So here we will be processing. So there it might happen if we might not have the left or right value, because binary tree can have most 2 child, but it can have only 1 as well, right? And then the other one wouldn't exist, and we don't want to call things on the none. So if self.left, if this exists, then only we will call our self.left dot display, and let's call the function on our level +1 as we are moving forward, 1 level up, and then we can send the prefix as left, or just call it L, you know, and then a little bit of space. Similarly we can call it on right. Okay, now we have our tree node ready. So I have deleted the previous things, so this will be easy now. So let's create the root. That will be our, also, you know what, let's call it our binary tree node now. Binary tree node, which root is 1, and then we will have left child. Let's call it left child 1. You know what, I'm gonna name these as with a number. Child 2 will be binary tree node 2. I'm just gonna create all the nodes right now as I can, as soon as possible. This will be 3, and then we can just, you know what, now we can create 4 and 5. 4 and 5 values, 4 and 5, and then one more, our 7. Okay, 7. Awesome. Let's define the relationship now. The relationship is root dot left will be equal to child 2 root dot right is 3. Okay, so this is right. So child 3. This is easy, right? Now root 3, child 3, child 2. Sorry, let's process child 2 if it is here. Left, what it would be? It would be 4. So child 4, and then child 2 dot right would be 5, child 5. Okay, one more, our 3 is remaining. So child 3 dot, this doesn't have any left, this only has right. So right would be child 7 Have we defined 7? We have defined, but we did not name it like this. So we can make mistakes, and we're taking it slow. You can fast forward the video if you like, but I just want to take my time, studying, revising. So anyone who is following, you can take your time and write your own solution. Okay, for now we don't have the ability of saving this code, so do not refresh or switch because you might lose it. I will add it maybe later tonight. I will add it to our AlgoYogi functionality. Now root.display, let's call this function, and we can run it. The error we had was because of I wrote there was a type of value here instead of val. So now, okay, let's run it. Voila, beautiful, right? We have our root 1, then left is 2, and then its left is 4, right is 5, and then we have, okay, no, not this one, my bad, sorry. Yes, this is a binary. This is it. Okay, so this implementation is done. Now let's move on to tree traversal, and now at this point I'm thinking if we should dive into our problems before covering our tree traversals. We could do it right here, but now we will be covering the tree traversal over here as part of LeetCode problems as well. But before we dive into it, I just want to quickly show on a binary tree how these traversal will work, and I'll be using recursion for now, but later we will be diving into recursion and iteration as well, using stack and dequeues and everything. But for now, recursion implementation of Inorder, Preorder, Postorder is quite handy, so let's just simply cover that before. So to show this as a theory, we have already covered it, but now for implementation, I'll be using this tree structure over here. I've created the root is 1, the root node is 1, and then child 2, child 3 are these binary tree 2 and 3, and then child 5 and child 6 are also over here. And then now I have assigned root.left to child 2, root.right to child 3, and then child 2.left is child 5, and root 2.right is child 6, which we have over here, right? These are the, so now let's just simply go into Inorder. We have studied these in theory earlier. Okay, so let's implement these really quickly, the solution, and we can end this video, and then we will move to our practice problems. All the problems of trees we will be solving one by one and uploading the solution over there. Okay, so let's define a function. We're doing it outside the tree node class. Okay, so let's call it in order, and which will take the root. It will take the root, and we'll check if base condition in a recursive solutions. You need to have a base condition. So if root is none, which is null in other languages, we return. Otherwise, we will recursively call it on left. That's what we do, because first we want to process the left subtree, then the root, and then right. So we'll call it on root.left, and then I just simply want to print it. Simply want to print the root.val, and then I want to I think I've already copied it, so but anyway, root.right. Okay, so this tree, let's just call it on our tree that we have created here. Okay, in order, and then we're calling it on our root. Okay. Print is already happening, so we'll simply call it. So see, 52613, that should be the output of our Inorder, which is the exact same output that we are getting here. And you know, it's always going to the left, then root, and then right. And that doesn't only apply to one node, but also the subtree. And you have to process the left subtree or the left node, then the root, and then the right subtree or this left right node. Okay, so now let's just do preorder, which will be exactly same, just one difference. So I'm just gonna copy, you know, like let me just combine it and then implement our preorder. Preorder would be processing the root first, left, and then our left, and then our right. So that will be our pre. And at the same time, I'm just going to do the post order as well. You know, I just don't want to waste too much time over here. And this is it, post order. And now our root will be processed in the end. This is what happens in post order. So let's just do it, and let's also replace these. And now we can simply test our preorder. We have already tested. Preorder we have already tested. Not doing it. Okay, wait 1 sec. Preorder. Okay. We tested in order, but not preorder. But I have written it over here. So preorder should be 12563. So 12563. Voila. Processing the root first, left subtree or left node, right subtree or right node if they do not have any other children, and then test the post also. You know, let's not make any mistakes. Run it. It should be 5, 6, 2, 3, and 1. Awesome. Now level order traversal, we have to do it using either an array or the queue or stack or something like that. Yeah, stack is a good choice to do level order traversal. But in Python, stack and array, that both same thing. But I'll explain the logic over here. But let's just implement it quickly. So what happens? Okay, this is good. Now let's just define it. Level order or BFS. Calling it BFS would be better. Let's just call it BFS. It will take root, and then we can just have a base condition. If root equals to none, then we just return same thing as the other. You know, this is edge condition here. It's because this won't be a recursive solution. It's just an edge condition because we don't want to process if the root is none. Now we will have our let's just create our this queue, which we will simply call it let's say queue, and let's append root to it if it's not none. Right now, while we'll use a loop here, while our queue dot, you know, this is how, while queue, let's just call it queue. While queue, we can check the condition like that. If it has a length, then this will be true. If that is true, then let's process the root. Let's process the root. So what would be the root right now? That will be printed over here because we are doing the level order traversal. Okay, so if it is not making too much sense right now, so this quickly just cover the video. We will cover these things in detail while solving those problems, and that's the main objective of you know, making this video, is just simply revising those concepts. And then q dot value, Okay, now if we have left child, then we will append it to the, you know what, let's just call it node, and we're gonna q dot pop pop left. I think that's how we do it. Pop left. I just want to pop the topmost value of our, I think this is it. Pop left. We can search it. Left in Python. Yeah, this is okay. Small, not like that. Pop left. Yes, dot. This is how we do it. Yes. Okay. Now our node dot value, if node dot left, then we're gonna q dot append our node dot left, and same thing with right. And the way this is happening, guys, is what we are really doing is we go to one level, and of course we're going to come across the parent, and we append left and right both child into our processing queue, right, which only has root right now. We take out the root, we process left and child node, or the first left node. Then we process this left node as considering as a subtree, which is now it's a root, and then it might have more left and right child. So if we have right now, then we will be processing the right child. Okay, so we will be appending it to our queue, and we will only come out of this while loop when we are done processing until the last level. The way this will be happening is we are at root, we put it in our queue, we start our while loop, check if our queue is non-empty, then we take out that root, print the value, and check if it has left and right child, and then append it to our queue. And next time it will come back and process. For now it processed 1, then it will process 2 and 3, but while processing 2 first, because Q3 will be added, already 3 will be added to our solution. Now here at this point, while processing this, it will append 5 and 6 after 3, but next time it will come to 3, and then it will process 3, but it doesn't have anything. But the queue will not be empty right now, it will have 5 and 6 to be processed. Okay, let's just call it now and call it BFS, and we are sending root again. So okay, so I think there was some error over here, it's not recognizing on an array, because that's how we are doing it, but now I think this should work. So in any way, we wanna just pop the first value. Okay, so now let's try to run it again. Okay, so 1, 2, 3, 4, 5, and there will be, later more solutions regarding, printing this level or traversal or BFS and take a 2D array. Each array should contain all the values on that level. We will do those later as part of the practice problems, but now I think this is done. And binary search tree, let's cover it later sometime, but for now I just want to tell you guys, binary search tree is basically a binary tree. However, it got some properties, and those properties are for a binary tree to be binary search tree, all the values in its left subtree have to be either equal to or smaller than the root value, and that applies to all the subtrees, whether in left or right or wherever. And then the reason we have binary search tree is it makes our time complexities of searching inserting into a binary search tree. I mean, insert and delete, they're like later thing, but it makes searching a value in our data structure very efficient. It reduces the time complexity to log n, because the way they are stored is we go to the root and then we check if the root value is greater than or less than or equal to our value, and if it is equal, we return that. If not, then we cut down the other half of the tree. But in worst case, it could be big of n as well. You know why? Because what if our tree doesn't have right but only left, and we just have this increasing order of all the values, or decreasing order of, I meant to say, from root to leaf, or leaf to root will be increasing. That's how it's going to be. So then it's going to be the worst case would be big of n. However, in a general case, it's log n. Okay, so this is done. Now moving onward, I'll be moving to our practice problems, and here let me just get rid of this. We will be covering all the problems in our tree section. So we'll be starting with easy problems. Easy problems. I'll just make maybe like 5-minute videos on all the each easy problems, and I want to do it separately and not part of the video, because sometimes people just want to refer to one particular video, and then we will append the solution over here as well. So if you want to come back and later refer to it. So this is it, guys. There are about maybe I don't know, we'll have to count 50 plus problems should be here, and then let's do it. Let's get this party started, and see you in our this is what I was saying. These are Inorder, Preorder, Postorder, inverted binary tree, famous problem. We will be doing these again, okay, and in detail. So see you guys later. Bye bye, and please subscribe and comment down if you like the video. But most importantly, this is where we start solving problems on AlgoYogi. Great way to track your problems. Awesome way to practice, have access to these notes and implement the solution right here. And then I will be uploading more courses over here, and then mock interview is just a way of someday you just just want to have an improve your thought process. Just start the interview, read the problem, and then write your own function, create your own examples and inputs, and then call that function. Timer is here. You can make use of that. I don't know. These are the basic functionalities that an app should have where you're practicing these coding solutions. Okay, so next video, let's solve all the trees problems, and it might take about a week, but I will try to do this as soon as possible, one video after another. I'll be uploading it, and thank you so much. Love you. Bye.